Categorical variables are mainly used as grouping variables that describe categories of entities. In theory, a person or case should only fall into one category. Good examples would be pregnancy. So the person's either pregnant or they're not. Gender, because biologically a person's either female or male. That is an example of categorical variables. The chapter uses a Pearson's chi-square test and log linear analyses to look at the relationships among multiple categorical variables. In categorical data, we can't use the means or similar descriptive statistics because we don't have any variables that have been continuously measured, so we analyze frequencies instead. And we do this through contingency tables. In other words, we look at the number of things that fall into each combination of categories on the table. For the chi-square test used for two categorical variables, it is important that the assumption of independence of data has been met. In other words, each person, item, or entity must only contribute to one cell of the contingency table. So it cannot be used on a repeated measures design. Neither can log linear analysis. Also, expected frequency should be greater than 5 so that statistical power is not lost. When there are 3 or more categorical variables, we use log linear analyses. Log linear analyses is an extension of the chi-square test and has similar assumptions. As before, each entity should only fall into one category of the contingency table, and the expected frequencies should be large enough for a reliable analysis. Sorry. For this study, I'm interested in whether people can be trained to meditate during work. Here's the data set I used. So there were 100 people involved, and I tried to train them to teach meditation in the workplace by giving them either money or merchandise as an incentive for meditation-like behaviors. At the end of the week, I counted how many of the people could teach meditation and how many could not. The two categorical variables are the training incentive, so the person was either trained using money or merchandise, but never both of them, and meditation, so at the end the person could either teach or do the meditation or they just couldn't. So by combining categories, we end up with 4 different categories. For my log linear analysis, I also split the participants into 2 separate categories based on their gender, so female and male. I used categorical data analyses because the people were incentivized using either money or merchandise, which is one or the other. They were either female or male, one or the other, and they could either meditate or they couldn't, one or the other. And that is why I use this test. So now let's actually do it. So as always, I started by installing the packages that were necessary. Just going to do that over and over and over again. The Gmodels package is used for chi-square, and the maps package is used for log linear analysis like last week. And then here's where I library them. So I would actually already have these libraried, but for the purposes of this, I libraried them so that I'll have them in the future. Next, I attached my created data set, which I just showed you. And I tell R that training has 2 levels of merchandise and money, and then I tell them that meditation has 2 levels of yes, they were able to, and no, they weren't. And I use the data.frame function right here to create my data set, joining the 2 variables I just created and calling them med data to use for the chi-square analysis. Next, I entered my contingency table directly. There were 53 people given money, and 33 of them were able to meditate. This is for the money, and this one's for the merchandise. There were 47 people given merchandise, and 22 of them were able to meditate. So I created the 2 variables. The first contained the 2 variables for those given money, and then the next one that I just created was for those given merchandise. And now I'm going to combine them using the cbind into pp2 table. Now I'm going to check to make sure that the created table was correct, which is just very easy. It summarizes itself, and that is correct. That's exactly what I wrote in there. The columns represent whether the training was encouraged using money or merchandise, and the first row shows the people who weren't able to teach meditation at the end of the training methods, while the second row shows the people that were able to teach it. So that's what I see when I create my table right here. This is my contingency table right here. So money, merchandise, And this is the people who were able to meditate, that's the people who weren't. And this is the chart that tells you exactly what's in each cell. And each person is only in one of these cells. They're not in multiple cells. It's how we're able to use this data. And so it's pretty interesting. Like 53% were given money, while 47% of the people were given merchandise. Okay, and this is where we would see chi-square results and p-values, and that's the odds ratio. So then I was able to run this chi-square using the cross table function right here in the Gmodels package, and that's this. The contingency table I created was what I just showed you right here. It's obtained by using the CHISQ equals true, and the Fisher exact test is adding by typing Fisher true, so that's just right here, as you can see. Expected equals true shows the expected values of each cell of the contingency table, which is useful to ensure that the related assumption has been satisfied. So that's the frequencies. Remember, we can't have a frequency lower than 5. We use the S residuals option to obtain standardized residuals right here, and format equals SPSS so that the residuals can be displayed. The output first shows the contingency table, which I just showed you. For each combination of training encouragement of either money or merchandise, we are given in this order the number of people, the expected frequency, the chi-square contribution, the row proportion, the column proportion, total proportion, and standardized residual. The column total again tells us that 53 of the people were given money as an incentive, 53%, 47%, or 47 were given merchandise. 45% were not able to meditate at the end, 55% were. In the total of 55% of people who were, 29% were incentivized, given money, and 25 were incentivized, given merchandise. Of the 45 who couldn't, 23 were given money, 23%, or actually 23.8, and 21% were incentivized, given merchandise. We must check the assumption for the assumption that the chi-squares are met. The assumption is that in the 2x2 tables, which is what we're looking at, as I told you before, we have to look and make sure the frequencies are greater than 5. The second row of each column, of each cell shows the expected frequencies. We are able to see that the smallest calculated frequency is for 21.150 for people who are incentivized, given merchandise, and were not able to meditate at the end. Right here. Excuse me, right there. I'm losing my mind. Sorry, Stephen. This value exceeds 5, and so the assumption has been met. If I had found a frequency value lower than 5, the best remedy would be to collect more data to try to boost the proportion of cases falling into each category. Now, the Pearson's chi-square test examines whether there is an association between two categorical variables. So in this one, the type of training encouragement and whether the person was able to meditate or not. After reporting the contingency table, which is what we just looked at, it also tells us if the chi-square statistic, what the value is, and if it's significant, and the p-value. The Pearson chi-square statistic tests whether the variables are independent. If the p-value is small enough or less than 0.05, then we reject the null hypothesis that the variables are independent and gain confidence in the hypothesis that they are in some way related. The value of the chi-square statistic is given in the output, as well as the degrees of freedom and a significance value. The value of the chi-square statistic is right here, and it's 2.404, which is not significant, with degrees of freedom of 1, and p equals 0.121, indicating that the type of training incentive used did not have a significant effect on whether the person could meditate or not. The output also reports the chi-square with the Yates correction, and its value is 1.82, but Andy says that it's often best to ignore this test, although that it does confirm the result from the main chi-square test for us, because this is also not significantly statistic. The final test reported is the Fisher's exact test, which you examine by looking at the first version, the labeled alternative hypothesis, right here. True odds ratio is not equal to 1. where it reports a p-value of 0.159, right here, which is not less than 0.001, and therefore tells us that we should not reject the null hypothesis. Because the training method incentives does not have any effect on whether the people were able to dance or not. So that's what the non-significant values indicate between us. There's no association between the incentive type and whether the person could meditate or not. So there was nothing significantly found about their relationship. Now I'm going to prepare my data for the log linear analysis. I start by creating a new data frame, I start by splitting participant into female and male because that's going to be our third categorical variable. And this is where I use the data.frame to put the training methods, if they were meditated or not, and the participants, male and female separation, all into one new data set called one new data frame called log M and F data right here. And then, in order to see the effects of training methods on females and males separately, I used a subset function to create a data frame called just females, which included only cases for which the participant variable is exactly equal to the word females. And I did this for males as well, so this just separates them between males and females. So it splits the participants into two groups based on their gender. I then used the cross table function to create a contingency table of the variables training methods and if they meditated or not separately, first for females, which I just did, and then I did it as well for males right here. We'll go back up to here. The command uses prop.t function to equal false to suppress the total proportions. We also suppress the column proportions and the chi-square proportions so they don't appear in the output. Even though we looked at them before, we don't need to look at them now. We also specify to show the residuals in the SPSS format. The contingency tables are very similar to before, although smaller because of the things we omitted, and they're separated by the participant's gender. So the first table is for females, which is right here. And the second one is for males. We'll get to that one in a second. There were 50 females total right here. 27 were not able to meditate the end. 23 were. And there were 28 given merchandise and 22 were given money. We could also report these totals as percentages. So we'll go down here. And for males, there were 50 overall right here. 19 were given merchandise, 31 were given money. 18 were not able to meditate, 32 were. They could be reported as percentages as well. So in short, males seem to be more willing to meditate at the end than females, 32 people compared to 23. And then they're also more motivated by money than females. There's 20 males compared to the 13 females that were able to meditate the end that were motivated by money or incentivized by money. So next, I need to pull my cursor on down to right here. And this is where I bind the data together from both of the created contingency tables using the xtab function. And then I report it, and it shows the same results from before, but in a different view. Let's see. It's the exact same results as we saw before. That was when I created, that was when I created, this is when we see the same results. Sorry, excuse me for that. This is where it just says 18 females were given merchandise. And this was if they weren't able to meditate. And then 10 who were able to meditate were females given merchandise, while 12 were males. So it's just another way to look at it. Next, I completed a log linear analysis in which I started with the saturated model and removed effects until the model became significant, but what you will see is that mine doesn't. but hypothetically, when the model becomes significant, I go back to the last model before it that was not significant and interpret it because it will be the best fit I can achieve given the available predictor variables. You are able to see if the model is significant by looking at the change in delta p-value, which compares the two models you just created. If you find a significant value, then that makes the change between the last two models of the last change you made before obtaining a significant value. So therefore, the last model is the best fit for the available data. Using the created contingency table above using all participants, so the one we just did, the female-male contingency table that we created using the xtab function, I start by estimating the saturated model, which will fit the data perfectly. So that's what I'm doing here. And then I'm going to report it using the summary function. I called the model saturated and used the log-lm function to create it, which was based on all main effects and the interaction in the overall big contingency table called female-male contingency table. The summary function, which I just pressed, is what I used to report it. There's a likelihood ratio of 0, a p-value of 1, because it is perfect fit for the data. Next, we'll fit the model with all of the main effects and two-way interactions, or in other words, we remove the three-way interaction and we call it a three-way. So it's everything but the three-way interaction right here. Now we're going to summarize it to report it. The model has a likelihood ratio of 1.143 with 1 degree of freedom, and p is greater than 0.001 at 0.285. So now we're going to compare the two models that we created, the saturated and the one without the three-way, using an ANOVA function. We look at the part called delta, which is right here, which tells us the difference between the two models. The value equals 0.285, which is not significant. This non-significant result tells us that removing the three-way interaction did not make the model significantly worse fit to the data. Therefore, we would continue by getting rid of the two-way interactions at this time. So next I start by creating new models, getting rid of each two-way interaction. First I get rid of the training method and meditation interaction, then the participant and meditation interaction, and participant and training method. So I just created all the models, and now I'm going to do the ANOVAs, comparing the created models to the one we did before that doesn't have the three-way interaction. So for the comparison between the model not using the three-way interaction and the model without the interaction between training methods and meditation, the p-value is 0.207, so we can remove this interaction without the fit of the model getting worse. Now we're going to look at the interaction between participant meditation, the model without participant 1.6, which is not significant. So we can remove this interaction without the fit of the model getting worse. Have not had a significant value, that's why we're keep going. The next one is the comparison between the model without the three-way interaction and the model without the two-way interaction of participants and training methods. And the p-value is 0.117, which is not significant, so we can remove this one without the fit getting worse. We would continue until we reach a significant p-value, and then you would use the model before, but there isn't one. It's never going to be significant. So now I create and interpret the three-way plot because I'm pretending it was the best fit for my data. Mosaic plot, which plots everything in terms of frequencies and the percentages. I apply it to the created contingency table that includes both females and males, and the plot tells us what we already saw before in our separate contingency tables, so it really is very difficult to see, but I reported everything before. Now this is where we do our follow-up analyses. And so an alternative way to interpret a three-way interaction is to conduct a chi-square analysis at different levels of one of your variables. So to interpret our participant by training method, by if they were able to meditate or not, we could perform a chi-square test on the training method and meditative variables, but do this separately that were females and our participants that were males. This way we compare the results for females and males just as we did before with the contingency tables. This is done using the subset function, which I created before, so we already have it. That just separated them into females and males. And I would use the cross table function as before to run the chi-square on them separately. But instead of suppressing the columns and not including all reports, I include everything possible by putting the functions equal to true, which was how we did the very first one. Effect size are reported in terms of odd ratios, which are easiest to understand for 2x2 contingency tables. In my report, I reported the odds ratio before, but now we can report it for males and females respectively. So I just created this for my females, and so it does the chi-square right here, and this is where we look at the odds ratio, which is 2.549, and for males, it is same spot, 1.059. So for females, the odds of meditating were about 2.5 times more likely if they're incentivized using money, while for males, it was about 1 time more likely. And this is all of my work, and goodbye. If I can type.